Welcome back to the deep dive. Today we're getting into the nitty-gritty of Chapter 13 from Feynman's Lectures, Volume 1. It's all about work and potential energy, A.
That's right. And this chapter, well, it's really fundamental. Feynman connects Newton's second law, Feynman dollar, directly to energy conservation.
Which feels almost like magic sometimes, that conservation law.
Exactly. But he shows it's not magic, it's math. It's a direct outcome of Feynman's laws. He proves it.
Okay, so that's our goal here. We want to trace Feynman's logic so you, the listener, really get why kinetic energy plus potential energy stays constant in certain situations. Not just the formula, but the reasoning.
We'll cover the basics, like a falling body, then generalize work, talk about path independence, which is key for gravity, and even look at gravity from big objects like spheres.
Sounds good. Let's start with Feynman's section 13-1, the simplest possible case. Something just falling straight down.
Right, only vertical motion, constant gravity pulling down.
And we all learn the rule. Kinetic energy, $2, which is $12 mu EG2, plus potential energy at 2, which is many dollars, equals some constant value. T plus U all is constant.
But the real physics insight is showing this pops right out of Phi now. It's not a separate assumption.
How does he make that connection mathematically?
Okay, so think about how kinetic energy changes with time. Take the derivative of 2t with respect to time, $2.
Okay, using the chain rule.
Exactly. You find that dt, the rate kinetic energy changes, equals the force times the velocity, $5.
Right. Force in the direction of motion times speed increases kinetic energy. Makes sense.
Now, for our simple falling object, the force $5 is just gravity, which is mg. We usually take up as positive, so gravity pulls down.
So T dt equals Miller times the velocity, dollars.
And the velocity, in this vertical case, is just how fast the height dollars is changing. It's d dt.
Okay, so dTtt equals now dTt.
Perfect. Now, hold that thought. What's the potential energy? TP dollar.
It's dB dollar.
And how does it change with time? What's the...
Well, knowledge dollars are constant here, so it's
Yeah,
just m in dollar times the rate of change of height.
mg, exactly. Now, compare them. dt dt is mg ddt, and dt is plus mg dh dt.
Well, what equal or opposite?
Precisely. So if you add them together, dtt plus du dt equals all dollars.
Which means the rate of change the total energy to T plus U is 0. So T plus U dollar must be constant. Wow.
That's the proof right there. Potential energy isn't just some random term we invented. It's the mathematical partner to kinetic energy required by $5 for gravity.
Okay, that's elegant for the simple case. But things are rarely just falling straight down. What about movement in 3D, curves, paths?
Right. Section 13-2 tackles this.
Right.
We need to generalize. The rate of change of kinetic energy, dt isn't just $5 anymore. It's the dot product.
The scalar product, math BFB up, math BFV. So it's the component of force along the velocity vector that matter.
Yes, and this rate, math BFET, math BFCE, has a name, power. It's the instantaneous rate at which work is being done.
Okay, so power is the rate, and work itself.
Work is the total change in kinetic energy when you move something from point 1 to point 2. It's the accumulation of all that power over the time it takes to move.
How do we calculate that accumulation if the force and velocity are changing all over the place along some curvy path?
That's where the line integral comes in. You integrate the force dotted with the infinitesimal displacement vector, dr math BFSS, along the entire path, d math BFS, d math BFS step.
So basically you're adding up tiny bits of workforce component times tiny distance along every step of the journey.
That's a great way to put it, summing up all the tiny contributions of effort.
And the result is work, measured in joules. A Newton meter is a joule. We see related units too, like kilowatt hours on electricity bills.
Right. Power, kilowatts times time, hours, it gives energy, or work done, kilowatt hours. It's the same fundamental idea.
Now, Feynman really emphasizes something crucial about gravity here, path independence.
Yes, this is extremely important. For gravity, when you calculate that line integral, donk math BFS, between 2 points, the actual path you took doesn't matter.
So climbing straight up a cliff versus taking a long winding ramp to the same final height, gravity does the same amount of work in both cases.
Exactly the same. The calculation simplifies beautifully.
Right.
Because gravity, math BFS, 0, 0, 0, 0, 0, only has a vertical component.
Right.
When you dot that with don't math BFS, dx, d rho, z, o, z, only the d1 part survives.
So the integral just becomes dom ps dzz, which is donk doct ed, or dom doc space d twi wandal. It only depends on the start and end heights.
That property defines a conservative force. Gravity is conservative. The work done is independent of the path.
And this independence is why we can define a potential energy function, $1 medius, that only depends on the position, the height.
Okay.
If the work depended on the path, $1 wouldn't make sense. It's just a function of location.
Precisely. And the ultimate test. Go around a closed loop. Start somewhere, wander around, end up back exactly where you started.
Since $z equals z2, the work done by gravity must be 0. MEG z1 equals dollars.
Right. Work done by a conservative force over any closed path is always 0. Think about friction, though.
Ah, yeah. If I push a heavy box across a room and then push it back, friction opposes me both ways. I definitely did work, and that energy turned into heat.
Exactly. Friction is non-conservative. The work done depends heavily on the path length. Mechanical energy, T plus U done, isn't conserved because energy leaves the mechanical system as heat.
Feynman also briefly mentions springs here, right? Force $5 equals kxc?
Yes, another classic example. The potential energy is 12 T by 2 tail and 2. And if you calculate the work done by the spring force, it also turns out to be conservative. T plus 12 kL to 2 is constant if there's no friction.
Okay, so we have conservative forces like gravity and ideal springs where we can define potential energy, and T plus U1 is constant. Now, what about gravity beyond just near Earth's surface where dollars isn't constant?
Good point. We need the universal law of gravitation. The force magnitude is $1 gm_mr22, always attractive, pointing along the line connecting the masses.
So the force changes with distance. Can we still define a potential energy?
We can. We perform the work integral math BFS BSPFS for this 100-2 force, moving from some reference point, usually infinity, to a distance, Jerry.
And that gives us the potential energy formula.
The dottle R equals GMMR.
Why the minus sign? I always have to pause on that one.
It signifies attraction. We define potential energy to be 0 when the masses are infinitely far apart, 20 unities and 50. Since gravity pulls them together, they have less energy when they're closer. To get to 0 energy at infinity, the energy at finite hour must be negative.
Okay, that makes sense. You have to add energy, do positive work to pull them apart against the attractive force, so their combined energy increases towards 0 as tree always gets bigger.
Got it. And this 102 dwarf is also conservative. The work done moving between 2 points only depends on the initial and final distances, $1 and 22, not the path taken between them.
So the principle holds even for universal gravitation. Okay, now section 13-3, summation of energy, moving from two bodies to many.
Right. Imagine a whole system of particles, maybe stars in the galaxy or planets around a star. How do we handle the total energy?
Well, the total kinetic energy is easy enough. You just add up $12 mile V22 for all the particles.
True, but the potential energy, you can't just use the total mass somehow. Gravity acts between pairs of objects.
Ah, right. So particle 1 interacts with 2, 1 with 3, 2 with 3, and so on.
Exactly. The total potential energy, 1 total R, is the sum of the potential energies for every unique pair in the system. So it's a big sum. Some pairs G my MJ dero, where semi vire is the distance between particle dollar and particle dero.
That looks complicated.
It can be. But the amazing thing is, even for this complex system, the core principle holds. If you calculate the time derivative of the total kinetic energy and the time derivative of this total potential energy.
Let me guess. They add up to 0.
They do. It requires more involved vector calculus involving Newton's third law, action-reaction pairs, but the result is the same. dt plus dia total dero, total energy is conserved for the whole isolated system.
Feynman links this total potential energy to the work needed to build the system, doesn't he?
Yes, it's a really nice concept. Imagine all the particles are initially infinitely far apart at rest. Bringing the first particle costs no work. Bringing the second particle, you do work against the force from the first. Bringing the third, you do work against forces from the first and second.
Keep going until all particles are in their final positions.
The total work you had to do to assemble the entire configuration is exactly equal to the total potential energy we just defined.
So potential energy is like the stored work of assembly. That's a cool way to think about it. Okay, final section, 13-4. Gravitational fields of large objects, moving beyond point masses.
Yeah, this is where things get geometrically interesting. What's the gravity like near, say, a huge sheet of mass or inside a hollow planet?
He starts with an infinite plane sheet of matter, uniform mass per unit area, let's call it.
And he calculates the force on a test mass nearby. You have to imagine summing up the gravitational pull from all the little bits of mass at $U in the sheet. He does this by considering concentric rings of mass on the plane.
It's an integration problem. You add up the forces from all the rings.
And the result is pretty surprising. The net force is perpendicular to the sheet, as you'd expect by symmetry, but its magnitude is $5 equals 2 pi g mu.
Wait, the distance from the sheet isn't in that formula?
Nope. As long as you're close enough that the sheet looks infinite, the force is constant. It doesn't get weaker as you move slightly further away.
That is weird. Counterintuitive.
It really is. And Feynman immediately points out the analogy. The electric field near an infinite plane of charge is also constant, independent of distance. It's a consequence of the inverse square law nature of the force.
Okay, that's one example. The other big one is the spherical shell. A thin, hollow sphere of mass, dollars.
Right. Analyze the potential energy, and thus the force, on a small test mass placed somewhere nearby. First, consider the case where knowledge is outside the shell, at a distance $2 from the center.
What does the calculation show?
It shows that the potential energy is $1 equals dEmmRr, which is exactly the same formula as if the entire mass dollars of the shell were concentrated into a single point at the center.
Okay, that's convenient. It justifies why we can treat planets and stars as point masses for calculating orbits as long as you're outside them.
Precisely. But now for the really cool part. What if the test mass $, is inside the hollow shell?
What happens then?
The calculation of the potential energy $, inside the shell shows that it's constant. It doesn't change as you move around inside. It's equal to the value the potential energy has right at the surface of the shell itself.
Constant potential energy. Hang on. Force is related to how potential energy changes with position. It's the negative gradient or derivative.
Exactly. If the potential energy $, is constant inside the shell, its derivative with respect to position must be 0. The gravitational force on any object inside a uniform hollow spherical shell is exactly 0.
Wow. So if you were floating inside a hollow planet, you wouldn't feel any gravity from the shell itself.
None whatsoever. The pull from the closer parts of the shell is perfectly canceled out by the pull from the more distant but more extensive parts of the shell in the opposite direction. Again, this perfect cancellation is a direct consequence of the force being exactly 122.
That is genuinely elegant. It ties the physics directly to the geometry of the situation.
It really does. So let's recap Chapter 13 quickly.
We saw energy conservation isn't just a rule. It flows mathematically right out of full dollar.
We defined work using the line integral Saint Math BFS us, and saw that for conservative forces like gravity, this integral depends only on the start and end points, not the path independence.
That allowed us to define potential energy $2. We extended this to multi-particle systems, where total dollars is the sum over all pairs and equals the work to assemble the system.
And finally, we looked at large objects, finding the constant force near an infinite plane, and the really striking result: 0 gravitational force inside a uniform spherical shell.
That zero force result feels like one of the deepest takeaways. It just seems so neat.
It is, and it hinges completely on that inverse square law.
Which leads to a final thought for you listeners. Feynman showed this amazing cancellation for a 100-to-2 force. What if gravity wasn't quite 100-to-2? What if it was, say, $1, $2, and $1, and $34?
Would that perfect cancellation inside the sphere still happen? Would the force inside still be 0? Something to ponder. The geometry and the physics are deeply linked through that exponent.
Definitely something to think about. Thanks for digging into force and energy with us today.
Always a pleasure.
Join us next time on The Deep Dive. Keep exploring.